The example that I gave for the use of a rigid bar element was a weld between 2 points on plates that are separated by a distance. But there are many situations that are even larger and more complicated than that. Perhaps an engine. Let's suppose that you had a model of an engine that was developed for some other purpose, perhaps stress, local stresses in one of the cylinders, let's say, and it has 20,000 degrees of freedom. And you'd like to build that into your automobile as a system model, and therefore you are not going to get much flexibility in that engine. You might as well treat it as a solid, rigid body. The RBE1 element is such an element that would characterize general rigid body movement. This allows connection of an arbitrarily large number of grid points, but you still have to have a set of degrees of freedom that will control the 6 rigid body modes, and generally you would have 6 degrees of freedom. These can be distributed out among the coordinates in the body, choosing even perhaps 1 degree of freedom at one node and another at another node. But again, you have to do this very carefully so that you don't over or under prescribe the constraints that are required. I find this reasonably tough to use and prefer the next implementation, which is the second rigid body element called RBE2. Another rigid body element would be one that would be controlled by the displacements at just one grid point. In MSC Nastran, this is the RBE2 element, and it allows you to control a larger body through the degrees of freedom at just one grid point. The card that is used is first the RBE2 card, an element identification number, and then the grid number of the controlling or the master node, then the coordinates that are going to be controlled in the other grids in the body, and then the list of the grids that are being controlled, which would be the remainder of the body. And then that list has to be continued on, of course, because normally there would be quite a few such grid points involved. Another rigid body type of element to be discussed is one that distributes load. The MSC Nastran RBE3 element is called a weighted average constraint element. And a typical use of this is to have a shaft in a bearing well, and rather than creating elements to build some kind of a spider out to the nodes around the periphery, you can mention the master node here, and then mention the nodes to which it's connected, and then the forces on this center node will be distributed out among the surrounding points on the periphery. Now, you can also weight those according to how much area they represent. For instance, if these are unequally spaced around there, you might want to unequally distribute the load. The constraints among the displacement are a little bit esoteric to me. I don't understand this element. I haven't used it very much. And I don't believe it really builds in any compliance concept, such as causing the load to be borne more heavily on the stiffer part of the surrounding structure. That's up to the user to determine with weighted coefficients. And rather than that, there is some implied displacement constraint involved here, such that if the surrounding points move, then the central point is required to move consistent with that set of displacements. So I guess you can view this either from the inside out or the outside in. Now, it turns out that it's the degrees of freedom at this center point here, in this case, that are eliminated. Problem 1 in our problem session has to do with the energy in a solid element. This will work us over a little bit on the stiffness matrix and the virtual work concepts. This is an 8-noded hex element, and all the nodes are fixed except number 4, which is moved 1 unit in the x direction. Now, to do that requires a live load shown here. There's a certain 100 newtons to the right, 50 newtons in the y direction, and 25 newtons up that are required to pull that exactly 1 millimeter to the right without any y or z displacement. Now, following that, node number 4, the same node, is given a virtual displacement of minus 0.001 millimeters in the z direction, so it's moved downward with a virtual displacement. The question that we're asked is to find several kinds of energy in the body. One is the total strain energy in the body at the equilibrium position. Secondly, what is the virtual work that has been done by the external forces during that virtual displacement? And thirdly, what is the virtual strain energy absorbed by the element during the virtual displacement? So it makes us worry. It looks like that's a lot of information desired and not very much in the problem to help us find it. When I was in college at Iowa State, there used to be a humor magazine, and they often posed those problems of a woodpecker weighing 1 pound in a tree 10 feet off the ground, and the wind is 4 miles an hour from the west, and therefore, what is your mother-in-law's name? And it sounds a little like one of those questions. The solution now involves setting up the matrix, which is really in the form of a 24 by 24 stiffness matrix times the one experiment that we have with a deflection here of a unit value in the 10th degree of freedom and 0 values in all the other degrees of freedom. Well, fortunately, that has the effect of canceling out all the columns except the 10th column. So we're left really only with this one relevant set of stiffness terms. Then on the right side, we can put the applied loads in our experiment, and they were 100 newtons in the x direction, 50 in the y, 25 in the z. And when you look at that, you realize, we can solve for all 3 of these stiffness terms. Well, we solve those 3 equations for those 3 stiffness components and get 100, 50, and 25 newtons per millimeter. The experiment, in fact, was posed in a way that directly gives these stiffnesses because there was a unit displacement at only 1 degree of freedom, and then these were the forces required to impose that displacement. The strain energy expression is quadratic in the displacement field and involves the stiffness as so. We put in the experimental displacements on the right and the left. They'll have the effect then of canceling out the columns here when you post-multiply by these zeros, and the pre-multiplication has the effect of canceling out the rows, and you end up then with this value 1/2 of K1010, which is 50 Newton millimeters. The next question had to do with the external work done during the virtual displacement. We'll call that the external virtual work. And it's an interesting hybrid in that you use a full set of loads, but you use the increment of displacement from the equilibrium position to the virtually displaced position. Now that was a separate quantity called a virtual displacement and amounted only to minus 0.01 millimeters at that particular degree of freedom. it was in the Z direction, downward, and that corresponds to the force on the right that was plus 25 newtons. So you get the product of those two terms is minus 0.25 Newton millimeters. Now, the third question had to do with the strain energy stored, the virtual strain energy stored during that virtual displacement. And that turns out to be actually a balance here, that it has to be equal to the external work that was done during that virtual displacement. And then that directly equals the amount that we found up above. So in other words, the work done by the external force field is absorbed internally. Now in this case, they're both negative. Problem 2 is similar to the first one in that I'm going to look at the stiffnesses in a porous cube of material. This is a problem that's been contrived to show a solid with zero Poisson's ratio so that it uncouples some of the relations. Suppose you have a cube of material and it's clamped on the bottom surface, and then you do an experiment where we're going to raise the degree of freedom U15 by 1,000th of a millimeter, holding all of the other degrees of freedom fixed. So here I'll sketch the loads and the displacement field. And we see that this corner has lifted up and has the loads given around the top surface. Now there are no other loads needed, no horizontal loads, and there are no horizontal reactions at the base. So it's going to be a body such as a foam which has zero Poisson's ratio and all the forces are aligned vertically. The point is to find as many stiffness coefficients as possible. Our experiment will define quite a few of these stiffness coefficients directly. We can lay out the overall size of the problem, and the stiffness matrix itself is rather big, 24 by 24, which means that there are 576 components involved. The displacement vector has only the value 0.001 in the 15th degree of freedom. The force vector has several known live loads, as well as some specified zero live loads and some zero reactions. Well, we can directly solve then for some 7 of the coefficients that are non-zero, and they're shown here. The numbers are enhanced by a factor of 1,000 because there's only 1/1000th of a millimeter of deflection that has been caused. Also, you can determine that there are a lot of zero terms because of the zero horizontal forces throughout the body. In total, then, you get 39 coefficients found directly in this way. But in addition, of the 576 such coefficients, if you now presume the material is isotropic, you can flip this cube in any direction and do the same kind of loading. So by geometric symmetry, we probably could find almost all of those coefficients. I'll leave that up to the viewer as an exercise to see how many more of these coefficients would come about by permuting the indices or flipping the body. Several years ago, I was approached by Hydrico Corporation of Kalamazoo, Michigan, in regard to a hydraulic valve that they had manufactured. It was a prototype valve, and it had failed during laboratory testing, short of the 2 million fatigue life cycles that they had wanted. They also were interested in raising the operating pressure of the whole hydraulic system from the level at that time to something higher, perhaps as high as 5,000 psi. So I'd like to discuss some of the concepts of the hydraulic valve as a small structural system modeled by solid elements, and at the end I'll make some conclusions about how you can scale the results for a family of bodies that are geometrically similar. Jim Glidden was a vice president for engineering at that time, and he had once attended the University of Michigan, so he was a little partial to coming back to his alma mater and seeing if there would be someone there that could analyze his valve. Lanny Becker came along also. This company is about a 2-hour drive from Ann Arbor, where the University of Michigan is. The company manufactures hydraulic equipment and does a lot of work for the makers of off-road equipment such as Caterpillar and John Deere and the car companies in addition. The hydraulic valve in question was a 3-bore valve. I've done a rough schematic sketch here to show that there were 3 holes bored through the basic block here, which is actually a casting, and in each of the holes you have 2 plungers. Now these plungers act as control valves, and they open and close certain passageways to the high pressure hydraulic oil. This casting itself is basically rectangular in shape. It is very intricately